Hello and welcome to this video in which we'll be solving a XAT 2024 question from the QADI section. And this is a geometry question. It's a very interesting question. I really like the question because it's definitely not among the easier questions in the paper. In fact, I'll say that to think about the solution of this question requires quite an in-depth conceptual understanding of the topic of geometry, and you need to have practiced geometry quite a bit to be able to decipher what all things can be done with the diagram here. And it might take also a bit of time to get to the correct answer. So I would say that it's a 2.5 to 3 minutes questions on an average to solve. And someone who has not practiced geometry will not be able to solve this question. What I'm going to do in this video is that I'm going to approach this particular question from two different angles. First, I'm going to give you a geometric solution to this question because geometry is a core part of that syllabus. Next, I'm going to give you a non-geometric solution to the same question. I'm not saying that the second solution is easier or tougher, but it's a non-geometric solution which uses pure trigonometry, but it uses trigonometry formulae from your 11th and 12th syllabus of mathematics. And I know a lot of students who take the CAT examination might not have taken math in the 11th and 12th. So what I'll do is I'll derive the required trigonometric formula using geometry methods to solve this question using the non-geometric method. Okay, sounds very confusing, but basically I'm going to be approaching the solution of this question in two different ways. Let's first understand the question. First, the question is telling us that we have a right angle triangle ABC, which is right angled at B. As I can see in the figure, there are two circles which are drawn with radius r. So both the circles' radius are equal. And they are drawn inside the triangle in such a way that one of them touches AB and BC. So AB and BC are tangents to the first circle. And AC and BC, the hypotenuse and the base, are the tangents to the second circle. The two circles are also touching each other. They're exactly touching each other at one point, which is an important piece of information to focus upon. And we have been given the lengths of AB and BC, and we have been asked to find out the radius of either of the circles. Right. So let me take this figure and let me tell you how to start thinking about the solution of this question. So if I look at the figure itself, I can see it's a right angle triangle. And first thing I can notice is that the lengths of the two sides are given to me as 18 and 24. 18 is 3 into 6. 24 is 4 into 6. And as soon as I see a right angle triangle, I should immediately think of the three sides of the right angle triangle and go to satisfy the Pythagoras theorem. And the two perpendicular sides are in the ratio of 3 is to 4. And we know 3, 4, 5 is the smallest Pythagorean triplet, which means the third side must be satisfying the 3 is to 4 is to 5 ratio of the three sides of the right angle triangle. That's the first thing to understand, which means that AC will be 5 into 6, which will be equal to 30 centimeters. Next, we know that both these circles have got two tangents, right? They've got AB and BC as the tangents for the first circle and AC and BC as the tangents for the second circle, which means that if I draw the normals, let's say if I take the centers of these two circles as P and Q, suppose. Okay. So if I draw the normals, if I say from P, if I draw a normal onto AB, and from P, if I draw the normal onto AC, we draw it properly. And from Q, if I draw the normal onto BC as well, and if I draw the normal from Q onto AC as well, then all of these will be equal to R. So this is R, this will be R, this will be R, this will be R, and all of these will be right angles as well. So clearly this quadrilateral is a square, and this quadrilateral is a kite. Let me name these points also. Let me call these, R, S, T, U. Okay. So these all constructions can be made. So when you have practiced enough geometry questions, you know that whenever there's a tangent, there's a normal. So you draw the normals, maybe they can be used in the solution of the question. Also, we have been given one more piece of information about the interaction between the two circles. The two circles are touching each other. So we should also know that whenever two circles are touching each other at a point, then they're points of contact. And their centers are going to be collinear, which means if I draw a straight line like this, if I draw a straight line joining PQ, then length of PQ will be equal to radius of the first circle plus radius of the second circle, so which means length of PQ will be 2r. Plus, because PQUS is a rectangle, so opposite sides of a rectangle are equal, so length of SU will be 2r as well. So all this piece of information I have. So from here, how can I solve this question? Can I use any piece of information, any piece of data to solve the question from here? It becomes very difficult. Actually, this is not enough to solve the question. One more thing that I have to remember, that whenever two circles are touching each other at a point, then to these two circles, we can draw three common tangents. We can draw two direct common tangents and one tangent through the point of contact. So I have a direct common tangent. BC is a DCT for both these circles. But what if I draw the tangent through the point of contact of these two circles? So if I draw the tangent, the common tangent to these two circles like this, let me call this, say, tangent to the point of contact as xy, right? Then this is another tangent that I can draw. And once I make this construction, then a few things get revealed to me about the solution of this question. Because now when I look at this triangle ABC, I can clearly see that inside the triangle ABC, XY is parallel to AB. And whenever you find straight lines inside a triangle which are parallel to a side of the triangle, you should immediately know that somewhere similar triangles concepts can and almost certainly will be used to get to the correct answer of the question. So drawing this tangent through the point of contact becomes crucial to solving this question. Once I draw this, I can see that triangle ABC and triangle XYC are similar to each other. What this means is that the ratio of the corresponding sides are equal, which means XY is to YC is to XC will also be equal to 3 is to 4 is to 5. Noting this is very important. Just like AB is to BC is to AC is 3 is to 4 is to 5, similarly XY is to YC is to XC will also be equal to 3 is to 4 is to 5. Now from here, we will do something which is absolutely counterintuitive to solving any quant question. And that's what makes this question not so easy. That's what makes this question slightly difficult. Is that we will introduce a proportionality constant and we'll take the lengths of XY, YC and XC as 3x, 4x, and 5x. Now, I'll tell you why this is counterintuitive, because you're already trying to solve this question to find out the value of a variable, for the value of an unknown, which is R. So introducing another unknown to find out the value of one unknown is not something that we generally do. What we generally do to find the value of an unknown is try to form an equation in that unknown. So that's the first thought process that will go through most students' minds, that what equation can I form in R? The fact is actually you cannot form any equation in terms of R. You can only do 3x, 4x, 5x, and you have to introduce this new constant. And now you have to find out some way to relate X and R, because I've introduced a new unknown. So to find out the value of R, if I need the value of X, I need some kind of an equation in X. So first thing that I'll try to do is I'll try to find a relation between X and R. For that, it's very important to note that in triangle XYC, the circle with center Q is an incircle. So circle with center Q is an incircle of triangle XYC, which means radius of the circle will be the in radius of triangle XYC. And we should know that the formula for triangles in radius is delta by S, area of triangle by semiperimeter. So R will be equal to area of this triangle by semiperimeter. And this is the concept. This is the formula we will use to form an equation between R and X. To get to this point is what is the point of inflection. So what is the point of inflection? There are three things that need to strike you in order to solve this question. One, you have to draw the tangent through the point of contact. Two, you have to understand that similar triangles have to be used and you have to introduce a new variable into this, or new unknown into the solution of this question. And three, you have to know that in radius formula has to be used. Everything else, everyone else can figure out. Anyone who has practiced geometry a bit can figure out everything else about this figure. But the three most important things that doesn't strike immediately, that we can keep in mind about questions like this from here on, is that we can draw a common tangent to the point of contact of two circles. We have to introduce a new unknown, and then we have to use a formula for introduce. So once I do this, because triangle XYC is a right angle triangle, so its area will be half into XY into YC, which will be equal to half into 3x into 4x. And S, which is semiperimeter, is sum of the lengths of the three sides divided by 2. So three sides are 3x plus 4x plus 5x, which is equal to 12x, divided by 2 is 6x. Now this 2 will get cancelled, and this 3 and 2 will get cancelled with 6. 1x will get cancelled, so I'll get R is equal to X. Very interesting equation. That makes the question so much more easier to solve. R is equal to X. From here, to find the answer to this question, to find the value of R, we just need one more equation in terms of R and X. And that is very, very easy to form, because now I know that YC is equal to 4x, which is also equal to 4R. And I know BC is 24, given to me. So BC is 24 is given to me. So which means that if I can find the length of BY in terms of R, I can represent YC again in terms of another value of R by doing 24 minus BY. So by's length will be equal to the diameter of the first circle, which is equal to 2r. So what I can see from here is that 2r plus 4r is equal to 24, which means 6r is equal to 24. And that will give me the answer as 4 centimeters. This is the correct answer of this question. This is how we can solve this question geometrically when we are completely using geometric concept to get to the correct answer. If you're satisfied with the solution, you don't want to learn trigonometry, you don't want to complicate your life, I can understand that. You can stop the video right here and you can use the solution to get to the correct answer of this question. But let's say, if you want to learn something about trigonometry as well, then let me uh, take you through a process that I'm really fond of. I'm really fond of trigonometry. I'm really fond of deriving trigonometric formula. What I'm going to do is I'm going to derive the compound angle formula for tan using geometric means. So I'm going to derive the formula of tan of angle A plus B using geometric means because I'm solving a geometric question, and then I'm going to use tan A plus B to solve this question here. So let's try to derive the formula of tan of A plus B. To do this, what I'm going to first do is I'm going to take a straight line. Let me call the straight line, let's say AB, of length 1 unit. Okay, suppose the length of this straight line is 1 unit. Let me not take capital A and B because I'm using capital A and B as points. So let me take the angles as small a, small b. Okay, I'm going to try and find out the value of tan of small a plus tan of small b. Then what I'm going to do is I'm going to draw a straight line from A, from point A, which is forming an angle small a with the straight line AB. Then from B, I'm going to draw a perpendicular, a straight line which is perpendicular to AB. And let's say the straight line which is forming an angle small a with AB is meeting this perpendicular line at P. Next, what I'm going to do is I'm going to take AP as a base of another triangle. And through P, I'm going to draw a straight line which is perpendicular to AP. So I'm going to draw a straight line which is perpendicular to AP through P. And also what I'm going to do is through A, I'm going to draw another line. What like this, which is forming an angle B with AP. Okay. And now through this point, through this third vertex of the right angle triangle here, let me call this point Q. Through this point Q, I'm going to draw a straight line which is parallel to AB. So this straight line here is parallel to AB through Q. Now, because this is parallel, I know that then this will also be a right angle triangle with the right angle at this place. And from this point here, let me draw, or from A, let me draw a straight line perpendicular to AB, which will also meet that straight line through Q, which is parallel to AB. So this will also be a right angle. Because parallel line and transverse system, interior adjacent angles will be supplementary. Let me call these 2 points C and D. So this figure is what I'm going to use to find out the value of tan of angle A plus B. Let me keep this on the side. Sorry. Let me keep this on the side so that there is no confusion with respect to the calculations that we are going to be doing from here on. Okay. So to solve this question, what I'm going to do, or to find out the value of tan of small a plus small b, what I'm going to do first is I'm going to try to find out the value of all the other angles in this figure. See this angle, angle APB will be 90 minus angle A. Right. So if this angle is 90 and the total angle BPC is a straight angle, 180-degree angle, that means that this angle has to be A again. Right? Because A plus 90 minus A and minus A will get cancelled. 90 plus 90, 180 will be the value of that angle. Okay. Next, because this angle is A plus B and CD and AB are parallel to each other, so this angle will be A plus B as well because alternate angles are equal. Angle DQA will be equal to angle QAB. Okay. So these angles is values I know. Now with this understanding, let me first focus on triangle APB. In triangle APB, let me find out tan A. I know that in a right angle triangle, tan of an angle will be opposite side by base, right? Opposite side by adjacent side, or perpendicular by base. In this case, perpendicular is PB, base is AB. Because AB is 1, so I can say that length of PB is equal to tan A. So length of PB is tan A. Let me make a note of that here. So this we have found out by applying very basic trigonometry. Next, what I'm going to do in triangle APB is I'm also going to find out the value of cos A. I know cos of angle A is base by hypotenuse or adjacent side by hypotenuse. So adjacent side here is AB by AP. So AB is 1, which means AP I can say is 1 by cos A. Let me make a note of that here as well. So AP is 1 by cos A. Right. If this is clear, I'm going to delete this because I have to do a lot more calculation here. So I hope this is clear. Length of PB is tan A, length of AP is 1 by cos A. Next, what I'm going to do is I'm going to find out the value of tan B. Or let me make this very clear. Let me remove this. I'm going to consider triangle APQ. In triangle APQ, I'm going to find out the value of tan of angle B. Now say tan of angle B will be again perpendicular by base, opposite side by adjacent side, which is equal to PQ by PA. Now length of PA I know is 1 by cos A. So length of PQ then cross multiplying will be tan B and B by cos A. So let me make a note of that. Length of PQ is tan B by cos A. Okay, pardon my bad handwriting. I hope it's clear enough for all of you to understand. Length of PQ is tan B by cos A. Okay. Right, if this is clear, next we are going to be moving on to triangle PQC. In triangle PQC, first I'm going to be finding out the value of cos of angle A. So in triangle PQC, cos of angle A will be adjacent side by hypotenuse, which is equal to PC by PQ. Now see, PC is tan B by cos A. Sorry, I mean PQ is tan B by cos A. So if I cross multiply cos A and cos A will get cancelled, which means length of PC will also become equal to tan A. Sorry, tan B, not tan A, tan B. Because PQ is tan B by cos A and cos B will get cancelled. So length of PC is tan B. In this triangle PQC also, what I'm going to do is I'm going to find out the value of tan of angle A. So tan of angle A in triangle PQC will be opposite side by adjacent side, which is equal to QC by PC. Now see, PC is tan B, which means QC will be equal to tan A into tan B. So length of QC is tan A, tan B. From here, finding out the value of tan of A plus B becomes very easy. Because ABCD is a rectangle, opposite sides are equal. So if length of AB is 1, length of CD is also 1. So length of QC is tan A tan B, which means length of DQ is 1 minus tan A tan B. We write this slightly better. DQ is 1 minus tan A tan B. And similarly, AD will be equal to BC. Opposite sides are equal and BC is tan A plus tan B. So AD will be equal to tan of A plus tan of B. So in now triangle AQD, this angle is tan of A plus B. So tan of angle A plus B will be opposite side by adjacent side. Opposite side is tan A plus tan B. And adjacent side is 1 minus tan A by tan B. This is the geometric proof of compound angle formula for tan of A plus B. This is what we will be using in order to solve the question in the XAT paper using non-geometric means, using this particular formula of trigonometry. But then what I wanted to show is that trigonometric formula is also derived using geometric means. So at its very core, at its very essence, this still remains a geometry question. Right. If this is clear, then keeping in mind this formula, let me bring back the image of that question that we are going to solve. Right, now to use trigonometry to solve this question, what I'm going to do is, again, I'm going to take the centers of these two circles as P and Q. But this time I'm going to focus on the second circle, and from Q, I'm going to draw the tangents on BC and AC. Sorry, the normals on BC and AC. Normals of the tangents. And I'm going to call, let's say, these two tangents as QR and QS. plus I'm going to join QC. So when I join QC, we can clearly see that triangle SQR and triangle CQR are congruent to each other because of SSS congruency. Because CS and CR are tangents drawn to the circle from the same point, so they will be of the same length. QS and QR both are radius of the same circle, so they will be of the same length. And QC is a common side, so by SSS congruency, both these triangles are congruent to each other, which means this angle, angle QCR, and angle QCS will be equal. So if I take one angle as A, the other angle will also be A. So we are going to be taking angle QCR and QCS as small a and small a. And of course, I know that the radius of the two circles are smaller. Okay. Also, we know that this particular length is 2r. And if I produce a straight line and I join that to the center of this circle, and there is also r. So which means length of BR is 2r plus r, which is 3r. Which means length of RC is 24 minus 3r. Okay. So keeping this in mind, let's look at triangle ABC. In triangle ABC, I'm supposed to try to find out the value of tan of angle C. Tan of angle C is AB by BC, right? Opposite side by adjacent side. But angle C is tan of twice of A, right? Because A plus A, 2A. And AB by BC is 18 by 24, which is 3 by 4. Now I know tan 2A is nothing but tan of A plus A. So we can use the formula of tan of A plus B. So tan of A plus B formula that we just derived was tan A plus tan B. In this case, tan A and tan B both are tan A. Divided by 1 minus tan A tan B, which in this case will be 1 minus tan A into tan A, or 1 minus tan square A, is equal to 3 by 4. So if we cross multiply, we will get a quadratic equation. The quadratic equation will say 3 tan square A plus 8 tan A will be, or minus, wait, am I writing this correctly? Yeah, 3 tan square A plus 8 tan A minus 3 will be equal to 0. So we can now factorize this. It's a quadratic equation, and we can factorize this as 3 tan square A plus 9 tan A minus tan A minus 3 is equal to 0. So if we simplify and if we solve this quadratic equation, I'll get the value of tan A either as 1 by 3 or minus 3. Now, in a geometric figure, tan cannot be negative because in this geometric figure, clearly A is an acute angle, it is not an obtuse angle. And acute angle means that angle lies in the first quadrant, and in the first quadrant, tan is going to be positive. Right. So it cannot be in the second or the fourth quadrant because angle ACB is clearly an acute angle. So tan A will be equal to 1 by 3. So this is what I'm getting. The tan of angle A is 1 by 3. But tan of angle A, I can also find out from triangle QRC. Because in triangle QRC, tan of angle A is opposite side by adjacent side, which is QR by RC. Now I know tan of angle A is 1 by 3. And we know QR is radius of the circle. And CR, as we have written there, or RC as we have written there, is 24 minus 3R. So which means cross multiplying, I'll get 24 minus 3R is equal to 3R. Or 6R is equal to 24, or R is equal to 4. This is another way of solving the same question using trigonometry. So because geometrically solving the question can be a bit complex, as I said, there are things that you need to think of, some of which are counterintuitive, like drawing the tangent, like thinking of similar triangles, introducing a new variable, applying a radius formula. If all of that doesn't strike you, but if you're good with trigonometry, if you're comfortable with the concepts of trigonometry that you learned in 11th and 12th syllabus, you can actually apply that as well and get to the correct answer of the same question. Hope this was helpful. Thank you.